Okay, so let's talk about pods. What really is a pod under the covers? A container in Docker is really a thin veneer over Linux kernel constructs. So the history of containers in Linux is actually Google committed the code into the upstream kernel that allows containers to exist. And this is why Google is so prevalent in the discussion in the container world, is that they effectively built everything that Docker and Kubernetes is built on way, way, way back 15 years ago into the Linux kernel. And these concepts are called namespaces and cgroups. Cgroups allow you to provide resource consumption controls and requests on CPU and memory. So you can say, please allocate a certain amount of memory as a reservation to this particular namespace. And you can also limit it that will throttle the CPU. And if you exceed the memory, it will also kill the process if you exceed the memory allocation limits that you've defined with the secret. Namespaces are what provide the illusion of a container being like an isolated virtual machine. They effectively provide boundaries within the Linux machine that make it appear as though the process is on its own in a private machine. So some of the namespaces are the network namespace, which is sort of like having your own private VRF. You have as well as interfaces. So you have a local host interface, and you might have a single NIC card that might or might not have layer 2 access to other pods in the pod network. We'll talk about the constraints there. And it effectively has a default gateway, which is pointing to the outer host. There is all containers inside a pod. Now, a pod is created, the analogy of a pod is like a whale pod or a pod of fish. It's lots of these containers all swimming together. They only share 2 of these namespaces. They share the network namespace, which allows them to all effectively have the same IP, and they all have local hosts. They all share local hosts. And they share the IPC namespace, which is the System 5 Unix interprocess communication. If you have software that uses that, it tends to be a bit passé these days, but some software does require that. Every container otherwise has separate process ID namespace, Unix timeshare namespace, which is host names, a mount, which is file systems, users, which is the UID and GID mapping. So root inside a container does not necessarily need to be actual root. It could be fake root, and cgroups, which allows you to map these quotas and limits on compute and memory. Containers also can optionally share selected volumes. So when you define a pod, you define volumes. And then you can say, okay, well, I'm going to cherry pick certain volumes to be mounted at certain directories in my container. And you can designate which containers get which volumes. And are they read-only? Are they read-write? That kind of thing. Now, at the base level, a pod starts with a tiny container called a pos container. And then alongside that pos container are the container instances that you define in your pod spec, which are usually backed by an image in a Docker registry that is downloaded by the container runtime. The pos container is this tiny piece of 68 lines of C code that literally exists to just create the identity of the pod. It allows you to put the network namespace and IPC namespace around something, and this is what's called the pod sandbox, that then exists, and then I can launch the other containers that the user specifies alongside this pos container. So the pos container contains the IP address of the pod, it contains the network namespace, and it really just registers the Unix signal handlers for the containers, and then it goes into an infinite loop to sit there and do nothing. So you can think of it as like the init process, effectively, of the container.
Sure. So just to be on the safe side, so every pod has a single IP address, and it's shared by all the containers running on the same pod.
Yes.
So it's totally different from the Docker model where every container has a different IP address.
That's true. Yes.
Thank you.
Yes. The intent of this was that the sidecar pattern, which doesn't mean much any more than literally the notion of I have my main, say I'm running a Spring Boot app, which is a Java virtual machine. I might want to run something alongside of it, like a logging agent or maybe Istio, which would actually be the Envoy web server as a sidecar. The sidecar mechanism, by the way, is the entire way that something like a service mesh runs, is that I can run a layer 7 ingress egress gateway on every pod in my infrastructure. It's an example of somebody looking in the sky and going, what if? And saying, just because you can do doesn't mean you should, but that's what we're doing with service mesh. But it was a valuable thing that Google knew of in Borg, which is their container scheduler that they use to run pretty much everything, including Google cloud. And so they decided we want to make it so that a pod, it can be a single container, but we want to allow multiple containers, potentially sharing volumes, to all coexist and allow them to all have the same IP and easily find each other if we need them all to kind of ride and die together. Okay, so the pod network namespace. How is the pod IP allocated? Well, there is a IPAM plugin inside CNI, and it's either provided by your CNI plugin vendor, or that you use the out-of-the-box one called host local. And host local will say on a worker node, I will have a /24 dedicated to this worker node for pods on this worker node, and I will pick an IP off that list and assign it to a pod dynamically. They are ephemeral. You cannot set a static IP on a pod. You can't reserve a pod IP. If you need static IPs for egress, you need some other construct, whether it's a service, which is the typical ingress construct for Kubernetes. For egress, there is no Kubernetes construct. It really depends on your CNI provider. NSX has this. I think OpenShift has this ability to do static egress IPs. Otherwise, if you're egressing out of your cluster, it's going to be SNATed to the IP of your worker node. Your worker node will be the IP, and that is how it'll hit the network, which isn't always great if you want identifiable IPs on your broader network for firewall or policy purposes. Now, a pod can also escape its namespace. So you can make a pod act like it is just another process on the host. And you go, why would I want that? Well, if you're running software and you purely want to use Docker images and containers for its simplicity and distribution of software, I can download this code easily and I can run it. But I actually just want to run a process on my host, whether it's a system level process or it's anything, I can do that. I can say, okay, well, this pod is going to be on the host network, and it will not create a network namespace for the pod. It'll actually place the pod on the host namespace so that you can see all the virtual interfaces running on the host, and you can do whatever you need to relative to your access rights as the pod, your Linux access rights when I say that. There's also host port, and a host port is an ability to do a DNAT for a dedicated port on your worker nodes that will map to a particular pod port. There is a generic host port mapping plugin as part of CNI that works almost any Kubernetes cluster, and then some CNIs provide a proprietary way of doing this that might be more performant or add extra features. Cilium will do eBPF, for example. NSX will do Open vSwitch flow to enable this. Just be careful. Host ports are for certain use cases, but usually services are a better construct because you have to guess correctly. You have to say, I want to open this port, and that port needs to be open on every single worker node in your cluster because it will reserve it on every single worker node in the cluster and then delegate it to that pod. Is it something you really want, especially if you don't run that pod in every node in the cluster? It tends to only make sense with a construct called a daemon set, where a daemon set ensures that a pod runs on every node in the cluster. If I'm not using that, host port doesn't make a lot of sense because if I hit it on a node, it doesn't have the pod, it'll error out. It'll just say, I don't know what to do with this. Host path, as an example, also allows me for it to have a pod to escape my mount namespace and to actually, I still have a mount namespace, but it'll do bind mounting of directories on the outer worker host into the pod mount namespace if I want to do that. That is something you would only do for system level pods. It's not something you would almost ever give to an end user. An end user should never have host path access. It's too dangerous to the cluster. And all of these settings can be secured for privileged use. Pod security policies, as I mentioned, there's an admission controller that allows you to secure these settings coming in saying, given your role, I don't really want you to be able to use the host network. Similarly, there is something called the Open Policy Agent, which is a more generic rules-based language where I can do logical rules on these attributes inside my manifests. Was there a question?
Just a remark on the host network. If you want to run something like free-range routing daemon in a container, then you must use host network, otherwise it cannot modify the host routing table. So there are scenarios where if you want to run the system services in containers,
yes,
you must use host network and probably also host path.
Yep. And those are the legitimate use cases for it. I'm running my payroll app. No, I'm running free-range routing, or I'm doing NFV telecom type workloads, or I'm doing BGP for my SDN controller for like Calico for my cluster. Yeah, those run with host network, definitely. And that's legit, but you wouldn't hand that to a developer that is, building a PHP app.
No, definitely not.
I've seen everything. So let's talk about the constraints of the pod networking model. So let's talk about the mandatory constraints that Kubernetes defines that must be available on the pod network. And then we'll talk about the optional aspects that you can't be guaranteed. It really depends. So mandatory, the host network must have routable connectivity to the pod network. So if a process exists on a host, it's outside of a pod and it needs to talk to a pod, it needs to be able to do that. This is separate from policy. You might have network policy, distributed firewall effectively, IP tables or its Open vSwitch flows or whatever, that restricts this to some degree. That's okay as long as it's something that's set in Kubernetes manifests. The intent here is to allow what they call a flat network in Google parlance, but effectively, I don't want natting. I don't want random firewalls that I don't know about interrupting me. I want to be able to know exactly, I can talk to everything. And if I can't, there's a deliberate policy that explains why I can't. Similarly, all pods across all worker nodes are all routable to each other. All pods across all worker nodes are routable to the service network. The service network is actually is kind of a special network that only lives on the worker nodes. It's predominantly DNAT and SNAT rules that implements it. There's nothing else. It can be routable to the external network, but that's rare. All containers within a pod share the networking namespace. I mentioned this several times, but they all have the same IP. They all have the same routing table. They all have the same ARP table. The pod IP address is dynamic and never static. You can't reserve an IP to a pod. Now, what's interesting are the optional things, and this really depends on your specific networking on your cluster. Pods, are they routable to your host network? So the host network can get to the pod, but can the pod get to the host? Not necessarily. It really depends. If you particularly, for example, use an Open vSwitch based network, OVN or NSX or whatnot, or Antria, which is the open source one from VMware. You can say these pods are in a separate namespace, and you can, for all intents and purposes from a networking perspective, you have no idea what node they're on because the subnet spans several worker nodes, and therefore you can limit the connectivity to the worker nodes from that pod to prevent anybody from ever talking to the actual host network if you want. L2 adjacency. There's no guarantee you're going to get broadcast, unknown unicast or multicast inside your pod. Often it can be the case, but it's not always the case. It depends. And the part 2 we're going to do a Safari tour of all the popular CNIs, and we're going to get into all which ones do this and which ones don't. I'm just telling you here that you can't predict it unless you dig into what's being used. And then finally, subnet allocation. As I mentioned, it's common to have host local subnets tied to a worker node through your pods, but that's not necessarily the case. You can do different topologies if you'd like. You can do it based on a pod selector or on a namespace in like Calico or NSX. It allows you a lot of flexibility there. So what are the considerations? There's interfaces, and I'm going to do a traffic walk. We're like 2 slides away from a traffic walk, so you get some pictures. I'm just going to walk through this and get your notepads ready for any questions. Typically, a Linux virtual Ethernet pair, or a vEth, or a VETH, is provisioned to enable the plumbing to work inside a Linux server. So you get a pair of NICs in Linux interfaces. One of them will be placed in the pod network namespace and one will be in the host network namespace. That's typically how it works. Routing, there is infinite number of options here. Well, not infinite, but a lot of variability out there. Let's first of all talk about how does the traffic get out of the pod namespace into the host namespace? Because it has to get to the host namespace, even if it's going on some magic Open vSwitch SDN controller. You still need to get to the host namespace. So that's one of 2 options. The first is an L2 bridge is created on the worker node, and that can be the Linux native Ethernet bridge. It could be Open vSwitch. It could be eBPF defined. It also doesn't necessarily need to be a bridge. It could be a link local layer 3 routability where you do not have accessibility to a bridge on the outer host. It's purely you're talking to this link local gateway and it's pure layer 3. This is how Calico works. Calico does not do a layer 2 bridge on the host. Now then you're, okay, say I have a packet. I sent a packet out from the pod and I need to send it out to the host network somehow. Let's say it's pod to pod, pod A, and it's talking to, like I have a Kafka cluster and I'm replicating data across my pods. How does that get to my other pods on other worker nodes? Well, the default is pure layer 3 to the host network. So this is the default assumption baked into Kubernetes. And it assumes one of 2 things in your underlying host network. Either it assumes layer 2 adjacency so that you can just dump IP and the other nodes will listen and answer ARP requests for that and grab them. grab the packets, or it assumes that multiple subnets are allowed on a single VLAN, i.e. IEP aliasing. This latter assumption is very common on public cloud. Azure Kubernetes Service, for example, will plumb user-defined routes in the Azure VNet for the pod networks so that you can just dump the layer 3 packet to the network and it'll route it to the other worker nodes. It actually will advertise the pod ranges, which are host local in their case, to map them to different worker nodes. In most scenarios where you can't do pure layer 3 to the host network, you'd use encapsulation. So this is the most common for on-premise data centers, or for those that don't really want to expose all their traffic and pod routes on their cloud network. So VXLAN is very commonly used. Geneve is sometimes used, IPsec over GRE in some cases. It doesn't really matter what encapsulation technology you're using, but just note that there'll be some encapsulation as an option. And then finally, are my pods advertised? Am I using host routes or pod subnets? And really, it's not super common, but on public cloud, it is. Public cloud, as I mentioned, usually there's an SDN controller external to the cluster, which is your cloud. It's Google or it's Azure or it's AWS. And the cloud provider is going to plumb those routes with the worker nodes as the next hop directly in the cloud SDN. In the case of Calico, they actually put a bird, which is an FRR alternative BGP daemon, on each worker node so that they can advertise pod subnets to the external network if that's what you want. And it allows lots of possibilities for a pure layer 3 fabric to communicate efficiently to your cluster with the pods being part of the fabric as first-class citizens.